Good afternoon, all of you, and let us start today's session. And so I will introduce today's speaker. Is a well-known scientist and professor. So it's my privilege to introduce Professor Pradeep Kumar sir. He's a honorary adjunct professor at Pune University at the Department of Atmosphere and Space Sciences. He has a very renowned career, and he has done PhD in physics related to atmospheric science, and then he has done postdoctoral research at the University of Manchester, United Kingdom, and he was working from 88 to 2019 in Pune University, and he has established Department of Atmospheric and Space Science at Pune University. Also, he is known for establishing cloud physics laboratory at Pune University, and he also built another facility, scientific facility, cloud nucleation facility at the University of Toronto, Canada. And he also taught as exchange professor at Belgium University. So I'll summarize some of his achievements, and yeah, he's also a elected member of International Commission of Clouds and Precipitation, and he is a member of MOES review committees and DST and other scientific organizations. And it was national programs like IPEX. He has guided that program, and he was a steering member of that team. He has more than 14 PhDs and many students he has trained in this area, and he has many reputed publications, very reputed publications in this area. So with that, I will invite Professor for presentation. Thank you, sir.
Yeah, thank you, Dr. Unikrishnan. So I'll go into the full screen mode now. It's visible?
Okay, sir. Yes.
Okay, this is the first of my 3 lectures. I will start with the process of cloud formation, which is basically I'll be dealing with the droplet nucleation in this lecture. So what are clouds? Cloud is a visible aggregate of small water droplets and or ice crystals suspended in the atmosphere and can exist in a variety of shapes and sizes. And clouds are classified based on altitude and shape. That we all know that. But what is the most important for this? Because you know that in the atmosphere, all 3 phases of water exist. So phase changes of water plays the central role in your cloud microphysical processes in formation of these droplets and ice crystals. So water evaporating from the earth ascends up as an air parcel, and when conditions are right, the vapor condenses and changes phase to become a droplet or ice crystal. And droplets under right conditions change phase and becomes ice. So these are the various phase change process which leads to the formation of all these particles in the clouds. And now if you look at these phase changes, you have vapor to liquid condensation, liquid to vapor evaporation, liquid to solid freezing, solid to liquid melting, vapor to solid deposition, and solid to vapor sublimation. Now if this box which I have put here, this condensation, freezing and deposition, these changes on the left are in increasing molecular order, and they are the most important for your cloud formation process. Now if you look at the types of nucleation, there is a homogeneous nucleation without any aid of foreign particle, and heterogeneous nucleation which requires an aid of a foreign particle, which is basically a nuclei. Now if you look at homogeneous nucleation, formation of pure droplets from water without the aid of atmospheric particles, the first stage in its growth is chance collision by a number of water molecules in vapor phase to form a small embryonic water droplet. And when this small embryonic water droplet forms, there is simultaneously a formation of volume and a surface area, which is forming from your saturated water vapor at a constant temperature and pressure. So the change in the Gibbs free energy, which is due to the condensation, which is given by NV mu V minus mu L, which is the work associated with the change in the formation of this volume, where N is the number of water vapor molecules per unit volume of the liquid, and mu V and mu L are the chemical potentials. Okay, that is, chemical potential is if a single molecule is removed from a material in a certain phase with temperature and pressure remaining constant, the resulting change in the Gibbs free energy is the chemical potential of that phase. So mu L is the Gibbs free energy per molecule in the liquid phase, and mu V is the Gibbs free energy per molecule in the vapor phase. Now, so that was the work term associated with the formation of the volume. Now there is a work term associated in creation of the surface area of the droplet, which is A sigma, and sigma is the work required to create a unit area of vapor liquid interface, which we very commonly know it as the surface tension of water. So now if this transformation is an equilibrium transformation, then the work terms, both these work terms should be equal. That is, the work term involved in the creation of the surface area should equal the work term involved in the creation of the volume. So the Gibbs term should equal the surface tension term. So these generally they are not equal, and these work terms generally differ. So therefore there is a net increase in the energy of the system due to the formation of the droplet, which we call it as delta E, which is the difference between the work term associated with the formation of the area and the work term associated with the formation of the volume. So now from your basic atmospheric thermodynamics, it can be shown that this chemical potential that is involved, that is mu V minus mu L, that is the chemical potential in the vapor phase minus chemical potential in the liquid phase, that takes this expression kT natural log the vapor pressure upon the saturated vapor pressure. Okay, whereas E is the water vapor pressure and ES is the saturated vapor pressure. Basically, this term is the saturation ratio, and if you multiply it by 100, you get the relative humidity. So this is the saturation ratio term. So where ES you can get it from your Clapeyron equation, and E is the vapor pressure, which depends upon the vapor in the atmosphere. So saturated vapor pressure depends upon the temperature. So if I put this, substitute this, because mu V and mu L, you get it in terms of measurable quantities now here. Okay, what we can measure in the atmosphere, and you put it into that equation where I had this work term associated with the formation of area, and this is now the work term associated with the formation of the volume, and this is the difference in my energy, delta E. So if I take a droplet of radius r and I put it, then I put the surface area here in the first term, 4 pi r square, and this is my surface tension term, and I put the volume V, I substitute by 4 by 3 pi r cube, and so this is my work term associated now with the volume, work term associated with the area, formation of the surface area, and this is the difference in the energy. Now we can consider in this case two cases. One is when the air is subsaturated, and one when the air is supersaturated, and that depends upon your ratio of E upon ES. So first, when air is subsaturated, when your relative humidity is less than 100%, then E is less than ES, then this term ln E upon ES is a negative term, therefore your delta E will be positive. This means that the larger the embryonic droplet that forms in the subsaturated air, greater will be the increase in the energy of the system. So when a drop is forming, the energy will be large. And a system will normally reach a stable state by reducing the difference in the energy. So in this case, the energy is increasing by the formation of droplet in subsaturated case. So therefore, the formation of droplet is not favored in the subsaturated air by homogeneous nucleation. However, in the atmosphere, random collisions of water molecules are happening, and therefore very small embryonic droplets will keep forming, and will be evaporating. They do not grow to become a visible drop. So this process of collision will be forming these drops, but they are very small. And since it is a subsaturated air, they will be evaporating back, and it doesn't become a visible drop. Now, second case we take is when air is supersaturated. When air is supersaturated, when that is your relative humidity is going above 100%. So normally in the clouds, it can go up to 101.5% or 102% maximum. It can achieve that much. So in this case, your vapor pressure is greater than saturated vapor pressure, and therefore this term log of E upon ES is a positive term, and therefore your delta E in this equation, okay, it will be positive or negative depending upon R now, because this is a positive term, so this whole term is negative, but then this whole thing expression will depend whether delta E is positive or negative will now depend upon the R, the droplet radius. So if you take in subsaturated air droplets with, so if I plot this is the subsaturated condition where E is keeping on increasing, where delta E keeps on increasing with the formation of the droplet, and in a supersaturated air it varies with R. So it will keep increasing and it will reach a peak, and then it will keep on, it will decrease. So this is the supersaturated condition. So these two curves are here, which is the increase in energy. Okay, so droplets with radius r less than the small r will tend to evaporate, but droplets which manage to reach this size and grow further will continue to grow, and when it continues to grow, the energy of the system will keep on decreasing. So in the region r is equal to r, there will be droplets can grow or evaporate without any change in the energy of the system. So what we do is we try to get an expression by putting dou delta E by dou R is equal to 0 at R is equal to R. And so therefore we get the equation which is 2 sigma by nkt ln E upon ES, and this is called as a Kelvin equation. So this is the equation for the droplet. It tells you that is for what size droplet to remain stable at a temperature, at a given temperature, what should be the relative humidity required. Or if you know the relative humidity, then you can say that is what size droplet is achievable. So this expression can also be written as, you bring this term here, ln E upon ES. So E upon ES is equal to exponential 2 sigma by nkt R. So this I put it 5.1, where ES is the saturation vapor pressure over bulk water, which you get from the Clapeyron equation. So this is the saturation ratio. Saturation ratio is a function of exponential 2 sigma upon nkt R. So this expression we will bring in again later. So just keep in mind this equation. I'll bring it again later. So it can be used to calculate the radius of the droplet, which will be in equilibrium with air at a given water vapor pressure, and it can be used to determine the saturation vapor pressure over a droplet of specified radius. So that is the Kelvin equation. So if I do a calculation with that Kelvin equation, so this is on the x-axis is my drop size in micron, and on the y-axis is the relative humidity required. So this shows that even for a very small drop of 0.01 micron, which if you compare to the size of water vapor molecule is only 2.5 angstroms, which is 2.5 to 10 to the power of minus 10 meter. So compared to that, 0.01 micron is a very big droplet which I am talking about, but very small in the cloud scale. Okay, so for that small embryo to form, your relative humidity is required is typically around 112% of relative humidity. So if by homogeneous nucleation, by chance collisions, if the water vapor molecules are colliding and the embryo has to form, then in the atmosphere the relative humidity is required is very, very, very high. And such a high relative humidity is never observed in the clouds. Clouds maximum is about 1 to 2% supersaturation, that is 101 to 102% relative humidity. So by thermodynamic considerations, if a droplet has to form by homogeneous nucleation, it has to have several 100% of relative humidity, which is not possible in the natural clouds. So therefore, droplets in natural clouds do not form by homogeneous nucleation. So the classical problem of cloud physics is to explain that is why still the cloud droplets are formed when the ascending air parcel is reaching about equilibrium saturation. Generally, nearly at about 100% humidity, droplets are forming. So why that happens? That is the classical problem of the cloud microphysics. So we therefore look at the heterogeneous nucleation. So in the heterogeneous nucleation, in the atmosphere, cloud droplets form on the aerosols. And these aerosols are called as on which these droplet nucleation can happen is called as the cloud condensation nuclei. Aerosols are all we classify as condensation nuclei, and those which are hygroscopic and can form cloud particles are called as cloud condensation nuclei. So you have to differentiate between CN, which is the condensation nuclei, and CCN, which is actually the cloud condensation nuclei. So the rate of droplet formation is determined by the number of these CCN present in the atmosphere. So when water vapor begins to condense on this CCN, because CCN, one of the main requirements is they have to be hygroscopic particles. And CCN, we will call it as a solute. And so when vapor is beginning to condense on this solute, it will begin to dissolve. So when a solute is added to a liquid, some of the liquid molecules are replaced by the solute particles. So I've put here two figures here. Okay, the top figure is showing that is entirely my droplet is just only pure water droplets. But whereas in the bottom this one, these are all water molecules. This round I have put are water molecules, and this cross in this one is the solute particles. So what happens is, because the solute is present in the droplet, there is a lowering of vapor pressure. Okay, so this solvent is your water and solute is the CCN. So if the vapor pressure of the solute is less than that of the solvent, it follows that the vapor pressure is reduced in proportion to the solute present, and this effect can drastically lower the equilibrium vapor pressure over a droplet. So if a droplet is requiring a relative humidity greater than 100% to form a droplet, so if a CCN is there and it has dissolved, then it requires much less relative humidity for the droplet to form. So this vapor pressure lowering effect by the CCN plays a key role in the droplet nucleation process in the clouds. So the reduction of vapor pressure due to the presence of the solute, you can express it by a law which is in the chemistry, which we call it as a Raoult's law, where E prime is the equilibrium vapor pressure over the solution, E is the saturation vapor pressure over water of the same size and temperature, and N0 is the number of water molecules and N is the number of water molecules of the solute. Okay, we are talking about the same size droplet, which is pure water and solution droplet. E prime is over the solution droplet. So the reduction of vapor pressure due to the presence of the solute we are getting in terms of the Raoult's law. And generally these solutions are dilute because they are not concentrated solutions. In the atmosphere, if you look at it, these droplets are not at all concentrated solutions. They are all dilute solutions. So for solutions which are dilute, the Raoult's law, you modify it in terms of 1 minus N upon N0. And generally for these solutions, these molecules are dissolved, these dissolved molecules are dissociated and that is, you must multiply then this, modify this by multiplying this n by a factor gamma, which is the degree of ionic dissociation. That is, for per molecule, how many ions are dissociated into the solution. So generally, the most popular CCN in the atmosphere are sodium chloride and ammonium sulfate. These are the two most abundant, naturally occurring CCN in the particles in the atmosphere, apart from whatever is coming from other anthropogenic and natural sources also. But the dominant ones are ammonium sulfate and sodium chloride. And ammonium sulfate has got a ionic dissociation factor of 3 ions per molecule, and sodium chloride has an ionic dissociation factor of 2 ions per molecule. So we have to multiply that by the ionic dissociation factor, which is called as a Van 't Hoff factor. So the number of effective ions in a solution of a mass ms is the mass of this one salt, and capital Ms is the molecular weight of the salt, and Na is the Avogadro number, and so the N is the effective number of ions which you can find in a solute of a given mass. So the number of water molecules is given by N0. Again, the Avogadro number is there, molecular weight of water is there, capital MW, small mw is the mass of the water molecule. So mw can be written as 4 by 3 pi r cube rho L, where rho L is the density of the liquid water and r is the size of the droplet. So equation 6.1, now we modify it. That is the reduction of the vapor pressure, equation, that term that we modify it by putting this Van 't Hoff factor term, and this is expressed in 1 by minus b by r cube term. So here the term is dominated by 1 by r cube. Okay, and b is all this. This is the Van 't Hoff factor. Ms is the mass of the salt, molecular weight of water, molecular weight of salt, density of liquid water. So this is the b term divided by the r cube term. So this is 6.2. This again. So this is my equation 6.2, 1 minus b upon r cube. Now I combine it with the Kelvin equation. The Kelvin equation was that for the nucleation of a pure droplet in homogeneous form. Okay, that is the 5.1, which I had said that I will be bringing back this expression again later. Okay, this is E upon ES exponential 2 sigma upon NKRT. Okay, this is, we got it from the balancing the work term of volume and work term of surface area in the homogeneous nucleation. So I multiply this term with the reduction of vapor pressure term due to the dissolution of the CCN. So I multiply this and I get it in terms of, so this term I put it as A, 2 sigma upon NKT, I put it as A, so, and 1 minus B by R cube into exponential A by R. Okay, and NKT again I can modify it in terms of the gas constant RV and rho L density of liquid water content. That is again a thermodynamic modification, I can do it. So we can expand that expression, and to a good approximation, that is, we can write that equation in terms of E prime upon ES, which we call it as the saturation ratio over a droplet of radius r, into 1 plus A by R minus B by R cube, 8. So where A by R is the curvature term, which we call it as the Kelvin term, which expresses the increase in saturation ratio over a droplet as compared to the pure water droplet. And B by R cube is the solution term or the Raoult term, which shows the reduction of vapor pressure due to the presence of the solute. Okay, so you have two terms here competing. One is the Kelvin term, which is the curvature term, 1 by R, and B by R cube, which is the vapor pressure lowering term. and together it will control the saturation ratio over the droplet. So this curve, this, you can plot this for different droplet radiuses, because all the other terms A and B you can find out, and you can plot the saturation ratio versus R, and that curves are called as the Köhler curve. And Köhler curve shows you that is how the curvature Kelvin term, which tends to increase the saturation at the droplet surface, competes with the solution term tending to decrease it. So if I plot that, if this is this red curve, which is my curvature term. So for smaller droplets, you can say it is high. And this green line, which you can see, is my solution term. Okay. And it is low for smaller droplets. So as drop size is increasing, this green one increases, and my curvature term is decreasing, because as the drop is growing bigger, the curvature term is getting reduced. So these two terms are opposing each other, this curvature term and Köhler term, and the resultant curve you have is the Köhler curve. Now this is, I have drawn it on a large, this one, the size here is in nanometers. And now I'll expand this, because we want to see exactly what is happening to this blue curve when we are close to the peak. So if I look at that blue curve here, I expand it in the next one. Okay, so if I expand this one, this curve will be like this. It is peaking at a point where we call that as a critical radius, and where it has peaked, that we call it as a critical saturation. Now what the beauty of this is, that is, you can calculate, you can make so many curves depending upon the mass of your CCN, or what is the dry particle radius, what is the dry particle of your radius of your CCN. So this plot which I have plotted is for a sodium chloride particle which has a dry radius of 13.5 nanometer. So that is your CCN, which is actually dissolved by taking in the water vapor, and it is forming a droplet. Okay, and the mass of that, this 13.5 nanometer, is 2.207 into 10 to the power of 20 kg. So as the drop is growing, so this curve actually, what you are seeing is the saturation vapor pressure exerted by the droplet on the droplet surface. That is what exactly we have calculated by the Köhler theory. Okay, so now let me explain how this works. Suppose my ambient supersaturation is here. One point, I hope we are able to see this y-axis. Suppose I say it is 1.006 is my ambient saturation ratio. That is 100 point something. So then if a particle of 13.5 nanometer has ended up in the atmosphere, then it will be at this size. It will, if it grows, the saturation vapor pressure on it will increase, but your ambient is 1.006, so it will evaporate back. And if it evaporates, then again the ambient is higher, 1.006, so it will increase. So a dry particle radius of 13.5 nanometer, if it is ending up with in an atmosphere where the saturation ratio is 1.006, it will neither grow nor evaporate. Now suppose it is around 1.0073 or something. That is the ambient supersaturation. And if my particle of dry radius, CCN of dry radius 13.5 nanometer sodium chloride has ended up in the atmosphere, If it evaporates, if water vapor is condensed on it, if it evaporates, it will come back this side, but again your ambient is higher, so it will grow back. And if it further grows, if it grows any further, it is going down this slope where the supersaturation ratio on the droplet is decreasing, but your ambient is higher at 1.0073. So this drop will continue to grow. So a drop which is at the peak of this Köhler curve is said to have activated as a cloud droplet. So for like this, for any given chemical particle in the atmosphere, whether it is organic or inorganic particle, you can calculate, you can plot these Köhler curves, and you can find out what is the required critical supersaturation at which that particular dry particle can activate as a cloud droplet. And when that activates, what will be the size of the droplet? That is the critical radius. Now, the beauty of this is then you can further expand that equation, and then through mathematics you can arrive at a simple formula, so that for every particle you need not plot a curve to get this activation, critical supersaturation and critical radius. You can automatically put it through this equation where r star is the critical radius, which is under root 3b upon a. A is coming from your Kelvin term and B is coming from your Raoult term. And the critical supersaturation S star, so when is given by 1 plus under root 4a cubed by 27b. So for any particle, dry particle size in the atmosphere, any CCN, you can calculate the critical supersaturation. That means the supersaturation required for that particular CCN to activate as a cloud droplet. And when it is activating as a cloud droplet, what will be the size of the droplet? So this is the starting size of my cloud droplet when it is activated as a cloud droplet. So these two you can get it simply from by putting into this equation. You need not calculate every time this curve. Okay, curve gives you a very good understanding of how the particle is behaving, how the vapor pressure lowering effect is functioning. So that is important for learning purpose, but once you know what it is doing, you can use these two equations to get the critical supersaturation, the saturation at which. So for any given particle sizes of CCN in the atmosphere, and for different chemicals, you can calculate the critical supersaturation and the critical radius. So that is what I have put here. So if we know the dry particle size of the CCN and its chemical composition, it is possible to determine the supersaturation at which it will activate as a cloud droplet, and also when it activates as a cloud droplet, what will be the radius of the cloud droplet. Okay, so I have given here now two cases here. One is the case, this blue curve is for my sodium chloride and the red curve is for my ammonium sulfate, and both these I have taken the same dry mass of 2.207 10 to the power of minus 20 kg, but sodium chloride is having a dry particle radius of 13.5 nanometer, but whereas ammonium sulfate dry particle will be 14.4 nanometer for the same mass. Okay, so now in this case, if I have a case 1 here where this is my ambient supersaturation 1.008, and if you look at the curves, you will see that the sodium chloride curve is going well below the ambient supersaturation. So therefore, the sodium chloride particle of 13.5 nanometer will activate as a cloud droplet without any issue. But whereas this curve of the ammonium sulfate, it is going above the ambient supersaturation. So this will not activate as a cloud droplet. But if my ambient supersaturation is above 1.009, then both my particles will activate as a cloud droplet. So based on whatever is our ambient supersaturation and based on whatever are the measurements of CCN and the chemical composition you can determine that is what will be my activation ratio of my CCN particles in the atmosphere. Okay, so this is the first part of the cloud nucleation. Okay, so what I'm giving you as a take-home message is the cloud is a visible aggregate of water molecule droplets or ice crystals suspended in the atmosphere. Clouds are classified on the basis of height and shapes they take, and there are four modern fundamental mechanisms through which clouds can form in the atmosphere. That is, I think somebody must have covered it. And phase changes play a major role in the formation of droplets and ice crystals in the cloud. Droplet formation by homogeneous nucleation of water vapor condensation is not favored in a subsaturated air, as the energy of the system will increase. So energy of the system is the energy which is the difference between the formation of the work term associated in the formation of the surface area and the work term associated in the formation of the volume when a cloud droplet is forming. And in supersaturated air, even for small embryonic droplet to form by homogeneous nucleation, this relative humidity or the supersaturation required is very, very large, and such high supersaturations are never observed in the atmosphere. And in a heterogeneous nucleation, the vapor pressure over the droplet is lowered drastically due to the presence of a solute. And these solutes are basically your CCN particles which are there in the atmosphere, and CCN are only a fraction of the aerosols which are there in the atmosphere. So the condition is of the CCN is they have to be hygroscopic in nature, or at least hydrophilic in nature. That is, it should be able to coat a layer of water on it. Only then it can activate as a CCN. And when it is dissolving, then there is a lowering of vapor pressure which is happening on the droplet surface. And this lowering of vapor pressure in the droplet surface due to the dissolving of the CCN as a dominating effect in the droplet formation in the natural clouds. Okay, and if you take that vapor pressure lowering effect term and multiply with the Kelvin term, which was that for a pure water drop, then we get the saturation ratio, and that saturation ratio is dependent upon two terms. One is the Kelvin term, which is the curvature term, and the other one is the vapor pressure lowering term, and the resultant is the Köhler equation, which we call. And this Köhler equation, when we plot it, that shows you that there is a balance, or there is a opposite effect happening between the curvature term and the this vapor pressure lowering effect term, and the resultant will give you the Köhler equation, and Köhler equation will give you, that is, at what supersaturations any given dry size of particle or the CCN can activate as a cloud droplet, and when that is activated, what will be the size of the droplet. So this is the basic nucleation process of the entire cloud formation process. And this only thing gets complicated is by the chemistry part of it, because these aerosols are never in its own chemical form. They are either internally mixed or externally mixed. So in that case, these basic Köhler equations, they have to be modified to take into account that mixture of aerosols. Other than that, this is the basic of the nucleation process, cloud nucleation process. So the references which you can look into is, one is the Atmospheric Science, an introductory survey, Valescent Hobbs, and the other is the short course in cloud physics by R.R. Rogers. Okay, so I can take now any questions I can take.
Sir, in second last slide, I have a doubt.
Second last slide. Okay, let me go to it. Not this, no?
No, sir. You take it to this.
35?
This, no, 36.
Okay, this one. Okay, this figure you mean?
In case of ammonium sulfate, sir, you
Okay, wait.
taken,
Just let me expand it. Okay, now tell me.
yes, sir. In case one, you taken the ambient temperature 1.008. So in case of
Ambient supersaturation.
supersaturation 1.008.
Yeah.
So in case of ammonium sulfate, in case of sodium chloride, the cloud will be start. Okay, so you told below the ambient saturation.
Yeah, because sodium chloride, your critical supersaturation required is 1.00724. Okay, so that is below the ambient supersaturation. That will activate. Okay, but whereas for ammonium sulfate, your required critical supersaturation is 1.0089.
Okay, it's more than 008,
Yeah.
so that's why it is not activated.
And if you look at it, can you tell me that is which is the efficient one in this case? Definitely, it is sodium chloride.
Sodium chloride, yes, sir.
Okay, and if you look at the critical size also, when sodium chloride is forming, the droplet size is bigger. It is 96.5 nanometer.
Yes, sir.
Whereas your ammonium sulfate is only 78.6 nanometer. It requires a higher supersaturation, and its droplet size when it nucleates is also smaller compared to sodium chloride.
Yes,
right? Yeah, and both are having the same mass. Only the radius will vary because the density is different.
Yes, sir.
Right.
Thank you so much, sir. Yes.
So, any more, any other fundamental question you want to, anybody has? You can ask me, there's no issue.
Sir, can you tell a basic question I have? I'm very early stage of my research. Can you tell the Kelvin effect and Raoult effect, like in terms of surface? Like sometimes we consider it's a plane surface, curved surface. Can you explain this one?
Kelvin term. This is Kelvin term is 1 by R.
Yes, sir.
And this is the so this is the curvature term. Okay, so this is smaller. Yes. The smaller the droplet, the curvature effect is more.
Okay, sir.
Okay, if I smaller the droplet, the curvature effect is more.
Okay, sir.
As it is getting bigger, it is getting more flattened out. Right. So therefore, this term is decreasing. Okay. This is coming down. But whereas the solution that is more and more of water it is taking, it is dissolving. That is becoming. It is increasing here. It's going towards positive. Okay. So these two are opposing each other.
Yes, sir.
These two terms are opposing each other. So A by R is taken as the curvature term, and 1 minus B by R cube is taken as the vapor pressure lowering effect term, Raoult term.
Okay.
So there are a lot of problems you can do with this to find out really that is what kind of which kind of aerosols are more effective. Okay, you can look into because a lot of organics also are efficient as CCN. Okay, and then so a lot of things you can do, and this is the basic equation which is used, which I will come to later when this is the basic equation which is used to when you're calibrating your CCN counters. Okay, So this equation is so perfect that you can calibrate your CCN counters using this equation, using the test particles as either an ammonium sulfate or a sodium chloride as test particles of given radius to calibrate your actual CCN counter which is going into the field. Okay, so this is a robust equation which is there. Okay.
Yes, sir.
Yeah. So in my next lecture, then I will go for the once this is activated and as a cloud droplet, I will go for the further growth of the droplet till it reaches a raindrop size.
Okay, sir.
Okay, so that will be my the second lecture on. So with that, I cover the which we call it as a warm cloud process, and then in my third lecture, I will be going to the ice phase of it, ice phase of the cloud. So these are the three lectures which I will be covering.
Sir, I have again a small doubt. If cloud will not activate, then where it will where it will go? This particle, this drop, where it will go?
This will just remain. If it is not activating, it will be just as a aerosol particle. It will just come down, settling down or transport wherever it is. Okay, because see, sulfates are in sodium chloride is produced by the sea salt mainly.
Yes, sir.
And sulfate aerosols are coming from both anthropogenic as well as naturally occurring process. This sulfate particles are there, and but since it is in the atmosphere, it is neutralized by the nitrogen, and therefore it goes into ammonium sulfate form. So that is the abundant aerosols. Okay, two abundant aerosols. Apart from that, so whatever aerosols are not activating as a cloud droplet, they will be just either transported or they will settle down in the natural its own settling. It has got its own settling velocity.
Yes.
So one of this one in the Kypex, this one was to, apart from the CCN, was to get the chemistry of the whatever are the at that level with the aircraft. What kind of chemistry is there at that level, so that you can understand the basically Kypex was oriented towards the cloud seeding process. You look at the cloud seeding operations. So for that, you have to know what is the kind of chemistry is there, what kind of particles are there, and what kind of sizes are there, what kind of chemical composition the particle has, and then whether with how they are getting activated under the with the Köhler terms. So this is a part of the Kypex program. So this is the basic of the entire cloud nucleation process. Okay. Okay. So if there are, you can go through this, and any doubts you can ask in the next lecture also. Okay, my next lecture is on Thursday, where I will go for the once it has crossed the peak of the Köhler curve, then how the droplet is behaving. Okay, till you reach the raindrop size.
Thank you.
Okay. So, anybody has any other doubt? Okay.
Thank you, sir. Actually, so if anybody has any doubt, actually, please actually email me. So I will connect to you. And also, sir, actually, please suggest some books to students. Actually, they can read.
No, books I have given in the end. I have given both the books. Both that is Wallace and Hobbes. That cloud physics is entirely very nicely explained, and cloud physics by Rogers. These are the two.
Then we will. Yeah. Okay.
Very good books.
Then yeah. Okay. Then we will close this today's session. And
yeah. But you may not find this in all this in detail, because all this has come from my research work.
Yes, sir.
All the curves and everything and calculations, everything. Okay. Because since I've been working on nucleation, that has come from all those. Come from my own this one. You may, but you'll get very good understanding from Wallace
And next session will be on Thursday, and same time we can have the session. Yeah. Okay, sir. We'll close
Okay,
this.
right.
Thank you.
Thank you.